Welcome everyone back to 262A, Learning and Reasoning with Bayesian Networks. This is our lecture 15, and it's going to be part one of our discussion on causality. And let's get started by a motivation of why we need to worry about causality. And we're starting with this cartoon actually from Yuda's latest book, The Book of Why on Causality. I'll give you a pointer to this later. And the idea is there are three types of thinking or reasoning that humans do. One is based on observing or seeing, and the other is based on doing, and the third is imagining. And if you think about what we've been doing in this class so far, we've been really doing the first type of reasoning. It's also known as associational. This is the kind of reasoning that's triggered by observations. You see something, you observe something, and then you start thinking and making associations. An example of that would be, you observe that someone has a headache, and then you want to reason about, what is the probability that they have a flu? Everything we've done in this class so far is basically associational reasoning. And what you need for this is a distribution, which is a Bayesian network. When you go to the other two types of reasoning, you will realize that you will need more information. The second kind of reasoning, known as interventional reasoning, this is the kind of reasoning that is triggered by intervention. You going and really doing something, forcing something to be instead of observing it. Examples of that is, what would happen if we ban cigarettes? Now, banning cigarettes is an intervention. Would my headache be cured if I take aspirin? Take aspirin is an action, is an intervention. This is, as you see, a kind of reasoning that require different tools than what we've discussed so far, and a little bit more information than one we've used so far. And in particular, it would require causal information. So if you go from seeing to doing, you will need to start involving causality in the picture. We have been using causality quite informally and intuitively, and we didn't actually need it for anything that we've done so far, but that will change soon. Today's lecture will be focused on intervention. Now, the third type of reasoning, known as counterfactual reasoning, this is when you effectively start reasoning about different scenarios that conflict with each other, and that's why it's sometimes referred to as imagining. What would be an example? Someone smoked and they ended up getting cancer, and say, what if I did not smoke? Here you're looking at conflicting and alternating scenario. Someone took aspirin and it stopped their headache, and then they start to imagine a different scenario in which they did not take aspirin. Would they still not have a headache under that kind of situation? This is something that we'll discuss in the next lecture. These three levels of thinking are sometimes referred to as the layers or the rungs of the causal hierarchy. And the idea is, as you climb up the ladder, you're doing more and more sophisticated reasoning. Again, we will be covering today interventions and next time counterfactuals, and we will be following a similar theme for both topics. What we'll do is first we'll start with motivation. Why do you need it? Concrete examples. And in particular, why can't you just do it using the tools that we have developed so far? And then we will also talk about what additional information you need to do these types of reasoning, interventional and counterfactual, as alluded to already. A distribution or a classical Bayesian network will not do it. And then the bulk of the discussion will be based on two parts. How do we do it? But in the first part, we'll talk about how do we do it in an idealized setting? How do we do interventional reasoning? How do counterfactual reasoning in an idealized setting? What is an idealized setting? An idealized setting is when you have a complete model. And here I'm writing causal graph plus parameters. At level one, this would be a fully parameterized Bayesian networks. But realize here I'm insisting now causal graph, not just any graph. And we'll talk about this more later. So this would be the idealized setting so that we really understand mathematically what's going on. But then a substantial part of the discussion will be about how do we do interventional counterfactual reasoning in a practical setting. And a practical setting is where we have a partial model. What does that mean? That means you give me a causal graph without parameters, just the structure and some data that may not be complete, that may be missing some parts, and then we will show how we can do that. Now, I call it a partial model because the data may not be enough to fully figure out the parameters of the causal graph so that we have a complete model, but we can still do it actually. And that's really the bulk of what happens in causal inference today, is to be able to answer these kind of queries and do that kind of reasoning based on a causal graph and some kind of partial data. And you can see this now also gets into learning, right? Because there is some kind of a learning component there. All right, that's basically the structure of what we'll be doing in these two lectures. Now, next time, depending on time, we'll also talk about one additional topic, which is how do we do this also practically using tractable circuits, which we already talked about. And there's some very recent exciting results there on that front that we can go over. All right, folks, just let me also mention one thing. This material is not covered in your book. The slides will be hopefully self-sufficient, but I'll give you a couple of references before we move on. Our book has been focused on the first level, associational reasoning. Everything there is about reasoning with distributions, just like the original book by Ida Pearl from 20 years earlier. Now, if you want textbooks that cover the second layer and the third layer of the causal hierarchy, these are two recommendations. This is the ultimate reference, the technical reference, the causality book by Ida Pearl. And there is a more recent book, which is the Book of Why, which is more of an intuitive, high-level discussion of the subject that's meant actually for the general public. Some of my neighbors and relatives not in computer science have read this book. So this is technical, this is not technical. And another actually very useful resource is, which I'm going to be using some examples from, is this one. This is 2016, more recent. It's technical, but more gentle, lighter than this guy. So you can think of this as the little brother or sister of that one. And nicely, this is available actually online. So you can actually look it up on this link. All right, folks. So let's go ahead and get started. First thing, why do we need causality? What is the kind of thing that we will be doing next? And for that, I'll be using a concrete example to illustrate something that we want to do called the causal effect, computing the causal effect of some variable on another. And then we'll see why we can do it using the tools we have, and then we will get to the discussion. So we'll use this particular model or example about a population of patients that have cancer. They could be in early stage or advanced stage, and there's a drug they can take. And then there's the survival rate. Are they going to recover or die? And as you can see from the connections here, clearly survival depends on which stage the person is at, whether they take the drug or not. Now, there is an edge here that basically, if you look at the numbers behind this Bayesian network, you'll find that, for example, people who are at a later stage or advanced stage are more likely to take the drug than people at an earlier stage. And we're showing the margins here. We're not showing all of the details of the models, but I gave you a sense of what's going on behind the scene. Now, my interest is in finding the causal effect of the drug on survival. That's what we'd like to do. This is a fundamental quantity in layer 2 in interventional reasoning, and everything pretty much revolves around this notion of a causal effect. Now, if I give you this, and the only thing you have is the tools that we discussed in class so far, you'd be tempted to go and say, okay, let me find out. Let me put this, yes, someone took the drug, and see what happens, right? So you go and assert evidence here, and we're going to do this, and we're going to assert evidence. And then you see the survival was this, and then became that it went down. So you would be concluding that this drug is actually harmful, right? So this is your attempt at trying to see what is the causal effect of the drug on survival. And upfront, that's the wrong answer. In fact, this drug will end up being actually helpful, not harmful. And the problem here is the query you ask is the wrong one. And again, we'll explain this in detail in just a little bit. But just to give you a sense of what may have went wrong here, let's just play with this model a little bit more. So what we're going to do next is look at the subpopulations of people who are in early stage or advanced stage and see what happens for those, for that group when they take or do not take the drug. So here, what I did is I said, okay, let's look at the early stage group and did not take the drug. and look at the survival rate. And now I'm going to say, let's look at that part of the group that took the drug, right? And look what happened. It was 80% in this group. It's 90% in that group. So for this group, it did help, right? The drug did help early stage cancer patients. Let's do the same thing for the advanced group, right? Same thing. So advanced group did not take the drug. Look at the recovery rate or survival rate. And let's say they did take the drug and look. So it was 20%, 30%. So it actually also helped. So in this group, it helped. In that group, it helped. And that suggests that actually this is an effective drug. It does help. But look, the answer we got here was to the contrary. What's going on here? What's going on here is when you went ahead and on this network pressed this button here and said, okay, drug is yes, you have done associational reasoning, while what you want to do is interventional. And let me explain. Look what happened between these two pictures. Look at the 40%, 60%. When you said, okay, I saw someone who took the drug, that's an observation. I saw someone, I observed someone take the drug. Look what happened to this distribution. Now you're saying, oh, it's more likely that they are in the advanced stage, right? So this number that you're getting here is an association or a conclusion that's now driven by the fact that you're talking about someone who's more likely in the advanced stage. So the number change that you see here is a contribution of both taking the drug and the fact that someone is in the advanced stage. That's not what you want. What you want is to isolate the impact of the drug on survival without getting this part of the reasoning process. So you need to go to interventional reasoning. And we're going to show how you can do this next. But the gist of it is going to be that, as I said, you want to isolate the impact of this cause and just focus on what is the impact of that cause on survival. Now, just before we move on, the phenomena that I just showed you is discussed in so many different ways. It's known as the Simpson's paradox. You can Google it, you'll find the Wikipedia page, you'll find all kind of interesting examples related to this one. And of course, these screenshots are from our tool, SAMIAM. Okay, so now we're going to show how do you actually do the causal effect? How do you compute it? And what we're going to do next is we're going to look at, I think, 4 methods of doing it. They're all equivalent. They're all different ways of doing it. And you don't need all of them, of course, but we're going to go over all of them so that we really further our understanding of the semantics and what's going on before we actually go ahead and that's all going to be in the idealized setting before we go into the more practical setting. It's pretty simple. What you really need to do is you need to work with a modified model in which you basically remove the impact of this cause on drugs. So that when you basically are saying, I want someone to take the drug, that will not impact the stage in which, because look, if you pick a person from the population and say, go take the drug, that action should not impact whether that person is in an advanced or in an early stage. And the way you do this is very simply by killing the parents of drug. So we remove that particular edge. If it had more than one parent, we also remove them all. So now this is a root node. All right. Now, when we do this, we need a new CPT for this. The CPT for this will just be 100%, 0%, because I'm saying take the drug. If the action was different, then I want to use a different distribution. So this is the model that will be used to compute the causal effect. And now when I did this, I removed that particular edge and I set the distribution here 1, 0. Look at the survival rate in this case, 54%. That's the correct answer. It was 51 and now it's 54. So according to this model, the drug does indeed help. Okay, so this is the kind of query that we want to pose. And as you see, this query will not work. What we did here will not work unless you have the correct causal structure. All right, so we'll talk about this in just a little bit more. But just to put it in equations, in the original model, this was the CPT for drug, right? It was conditioned on stage. We got rid of this, and now we have a new CPT because it's a root node, and it's simply 1 and 0. So we basically nullified the previous causal mechanism, if you want to think of drug, and replaced it by this. Now, in this model, you can go and look at the causal effect in each subgroup. So you can say, what about the guys that are in the early stage? And you'll see the 90%. What about the guys that are in the advanced stage? Then you will see that there are basically 30%. And in both cases also that will increase from the previous thing. So this is our first core method for doing causal effect for reasoning about intervention. It requires working with a modified model, and now we're going to look at some more things and say quite a bit about this. Now, I just want to make one more remark before we move on and tell you about the other methods that we will be using to do the same thing. Here's the model we have. Look what we did here. What I did is I went and reversed this edge, right? So I built a different structure. Right, I messed up with the causality. Now, you would look at this and you think, yes, this is the right causal structure for this scenario. Now, this is not the right causal structure. But what I did is I parameterized this in such a way so that it will induce the exact same distribution as this model here. I'm not showing you the numbers, but you have to trust me. In fact, using the new parameters for this guy, you can see the marginals are exactly the same. And in fact, you can try other scenarios. You can go and say, oh, let me assume that someone recovered, and you can see how these got updated. You can do it here. You're going to get the same numbers, exact same numbers. Here's yet another scenario. What about people who are in an advanced stage and did not take the drug? And you look at the numbers here. You can do it here. You're going to say the exact same thing. My point here is, even though these two guys have different structures, different causal structures, they've been parameterized in such a way where they both induce the same distribution. Up to before this lecture, when we were doing associational reasoning, that is computing probability of X given Y, you could use either this or that and you'll be good, because the answers you'll be getting depend only on the induced distribution. And since these two guys induce the same distribution, you will be getting different answers. The only difference between different structures were computational, but not semantical. Right now, this is going to stop being the case. To do what we did, you need to know what the parents of the node is, the true causes, so that you can modify the model. If you do it on this, you will get the right answers. If you do it on this guy, you will get the wrong answers. So in summary, these are two models with different causal structures. They induce the same distributions. They are equivalent as far as answering association queries. They are not equivalent when you would actually be doing interventional queries. So this is something that's going to be very important. So now we're going to insist that you do have the right causal structures. And if you just tell me, I just got the right distribution, that's not going to be enough to do what we will be doing next. Another way that you will hear this same observation, Udapur says that a lot in his talks, is data is not enough if you want to do more sophisticated reasoning. If you want to do interventional reasoning, counterfactual reasoning, data is not enough. So let's try to take this statement and substantiate it. You have two different models. I just showed you two different models, M1 and M2, and they disagree on their causal structures, but they both induce the same distribution. Now, these two models will generate the same data. So if you look at this distribution and start sampling from it, you're going to see the same data. So whether you had this or whether you had this, you will be seeing the same data. So if you only have access to the data, you will not be able to tell which one of the two models generated that data. And knowing which one of these models generated the data, in particular their causal structures, is important for doing interventional reasoning and later counterfactual reasoning. That's why if I just give you access to the data, you will not be able to answer certain queries, all right? And this is what people mean when they say data is not enough for certain kind of reasoning. You hear this put in the context of criticism for a lot of AI techniques today that purely look at data and try to learn patterns from them. So what we need is further information. And in this particular context, what we need is the causal graph to augment the data so that we're able to do the kind of things that we want to do. So what I'm going to do next is still continue to operate in the idealized setting and show you a few more ways of doing the exact same thing that we did which will give us even further insights into it. So any questions at this point? All right, so let's keep moving. So how else can we do this? This is what we did so far. We said, delete the parents of the variable we're intervening on, set its simple CPT now based on the intervention you want to do, and keep going. And that entailed, again, changing the CPT for the variable we're intervening on from this to that. The next method I'm going to show you is, we're going to call it method 2 for now. I'm going to add an auxiliary node to the original model that represents my intervention, because you can think of an intervention as yet another cause for taking the drug. So in this case, the cause was what stage you're in that will cause you to take it. But this is me basically saying, I'm going to force you to take it. So we can add it as an auxiliary node and represents this intervention. Now, when we do this new model will need two things. It needs a CPT for this, and we have to modify the CPT for drug. The CPT for this, which is just a prior, can be anything according to this model, as long as it's not extreme. Just don't put 0, 1, or 1, 0, just anything. In this case, we put 50, 50. Now we just have to show you how to modify this. And the modification is in the way you would expect it. If do is no intervention, then this distribution, given that, would be as it was before. But when do is yes, then this will just be yes, and this will no longer be relevant. So let's look at it. Here it is. So this is the original CPT. It was drug given stage, and now the new CPT is drug given stage and do. So we have two situations. When no, then this new distribution is just like the old one. So as if I haven't done anything. So I'm kind of nullifying this node. But when do is yes, then the distribution on this is 1, 0. So it's just saying I intervened, okay? And so the drug must be yes because I did force it to be yes. So that's straightforward and can be automated. Now, if you have this augmented model with this additional node, then if you go ahead and say no, you assert evidence no here, you get back your original model, right? So it's as if like you didn't have this node. And in fact, you can see the marginal zeros are exactly the same as they are there. So setting this to no brings you back the original model. But if you want to emulate intervention, you can go and set this guy to yes. And that's what we're doing here. And then this will give you the same results that you're getting here. Now, look, interestingly enough, before, when I went and did drug yes, what happened to this marginal? It changed. These numbers change. In this case, they're not. When I did do an intervention, right? This is, I'm forcing you to take the drug. That didn't really change our belief about what stage of cancer you are. It's still exactly like it was here. This is our method 2 for doing it, and it will have the same exact result as the previous one. All right, folks. So what we want to do now is just look again at method 1. We looked at two methods now. The method where we delete the parents and the method where we add an auxiliary node. I'm going to look at the standard method where we delete the parents and show you an algebraic view of what's going on. In particular, we will look at the distribution induced by the original Bayesian network. We have a formula for that. That's known as the chain rule of Bayesian networks. And we're going to look at a similar formula that we can use for this guy, which is known as the truncated formula. And the reason we need to look at this, because if you have the chain rule or the formula based on the chain rule that shows the distribution that you originally had, you can modify it in a systematic way to get the formula that expresses the distribution for this guy, which we're going to call the interventional distribution. And here how it is. So there are two lines here. One line is for the formula that specifies this distribution. And the second formula is the interventional distribution induced by this guy. So let's look at the first one, which we are familiar with because we spent quite a bit of time with it. This is, we're talking about the probability of survival, drug, and stage. Probability of a full variable instantiation. We know how to do that, right? Chain rule. In this case, survival given drug and stage multiplied by the probability of drug given stage multiplied by the probability of stage, right? We have one component for each node. We know how to do this. Now, the second formula, first of all, note notation.
if this was the original distribution, the interventional distribution will be notated by this. That is, what is the new distribution now that I fixed drug to yes? And it's going to be over the remaining variables, survival and stage. Now, here it is. I can get this systematically from that using a two-step process. First, the term or the component that correspond to drug, which is the variable I intervened on, I drop it. It's gone. Now, I still have two more in this case, and in general, I may have more. Anytime drug, which is the variable I intervened on, appears in one of these components, I will fix it to yes, which is the intervention that I did. It does appear here, so now I'm doing drug equals yes. It doesn't appear here, so I carry this as is. Now, this is the distribution induced by this modified network, and this is known as the truncated formula of the interventional distribution. All right, so I hope this is clear. Two things you do. You drop the component that correspond to the variable that you intervened on, and you fix its value according to the intervention in the other guys. All right, so now we have method one, method two, and we have a formula that shows what method one is. So if we want to summarize what we did so far, we've been operating in a complete model setting. I do have the fully specified Bayesian network with the right causal structure, not any kind of structure. It must be the causal structure. And we looked at the method one, which people sometimes refer to it as the surgery method, because I did surgery on the graph by removing these parents. And the second method is the auxiliary do node. We added this auxiliary node. And the third method is the truncated formula, which is just another view of what happened here. All right. So now we're almost ready to go to the second part, which is how do I do this in a more practical setting where I do not have the fully specified model, but I have just the structure, causal structure, and data. But before we do this, I want to show you actually one more method of doing this. This method can be viewed as belonging to part one or part two. We're going to look at it twice, actually. And we're going to look at it in part one first because it will give us a nice bridge for the second part of the lecture. So let's go ahead and do that. And just before we do that method, I need also notation that we're going to use for the rest of the lecture. What we've been talking about, the causal effect, we've been talking about it somewhat informally. The causal effect of this on that, that is, if I fix the value of variable X to this value, what happens to Y taking that value? That's notated this way. The probability of the variable Y taking that, given that I do this, right? As opposed to observe. Before we didn't have the do, we just have a conditioning bar, and then we put X equals small x. That means given that I observed X to take that value. Now, given that I forced X or intervened to make X take that value, that's a temptation. Or simpler like this, as we do. Sometimes we drop the variable and just do that. Another notation is this. Okay, this may look quite weird. You say, why would we need this? Why is that not enough? It turns out that this is actually end up being useful when we do counterfactuals. It ends up being handy notation. So for the rest of the lecture, we're going to either use this or that. All right, so Y subscript X, that means probability of Y given that I fixed X to that particular value. Okay, you need to memorize this notation. This is very important. The other piece of notation, we use this to talk about the distribution of a Bayesian network. And if we want to talk about an interventional distribution, we're going to use this. So this is the interventional distribution when I fixed X to this value, and it will be a distribution over these two variables. All right, so remember this, distribution, interventional distribution, and this is the causal effect. All right, okay, let's do one more thing, and we will take our break so we come back and do part two. The one more thing I want to do for showing you how can you really compute the causal effect is something known as the causal effect rule. And now that we have our notation, we can start writing formula instead of just doing it informally. So I do have a fully specified causal structure with numbers, and then I want to compute this causal effect, right? Causal effect of X on Y. And I'm using both notations here. Now, this rule is pretty simple. And it says, if you have the parents of X, and let's call these Z. So Z happens to be the parents of X, then this is equal to that. Okay, I want you to stare at this formula. There's very important points we're going to make about it. But first, let's just look at it. What it says is sum over all possible values of the parents, and then do this. Y given xz multiplied by the property of z. Now, the key thing about this formula, the key thing is on one side, you have an interventional probability that is layer 2. But on this side, you only have associational probabilities from layer 1. So what this formula is saying, given these associational probabilities, I can actually compute an interventional probability, right? Expressing interventional probabilities using associational probabilities. Now, this is going to be a theme in the second part, but then you may say, oh, wait a minute. Didn't you tell us multiple times that we can't do that? That if I just have the distribution, I shouldn't be able to compute interventions? What's going on here? Isn't that a contradiction with what was said earlier? What's the catch here? Anybody? What is the catch here? I'm showing you a formula in which on this side, I only have association probabilities, and then suddenly I'm using them to compute the causal effect. Aha, someone is saying, yeah, you gotta be careful. You cannot use this formula unless you know the parents. And knowing the parents means you have to have the right causal structure. So to apply this causal effect rule, it's not enough to have association probabilities. You also need to know what are the parents of X. And that's the extra information that we need here. Now, if you have the right causal structure, then you will know what the parents are, and then you can apply this. If you have the wrong causal structure, you will have the wrong parents. So if you plug them into this formula, you're going to get the wrong answer. All right. So to use this formula, you need to know the parents, and that's the additional information you want. When we get back, what we're going to do is you're going to give me causal graph, no parameters, and some data. And then you're going to ask for a particular causal effect. And then I'll show you how to compute. Now, we have to make a few points before we move on. First, when you give me a causal graph and data, and you ask for a particular causal effect, sometimes it may not be possible to do the computation. Provably. That is, based on the causal structure you gave me, the causal graph, and the data that you have, and the particular causal effect you're asking for, I can prove to you no one on earth can actually do that computation for you because you don't have enough information. Now, when it is possible to compute the causal effect based on this information, then we will say that the causal effect is identifiable. That's a very important term. And identifiability is a big deal. In fact, we will look at several methods that will check whether a causal effect is identifiable. That is, whether it is possible to compute it from this kind of information. And these identifiability criteria not only come back with a yes or no, and when they come back with a yes, they show you a formula for doing it, like a formula like the one we've shown before. There is a formula that on the right side have only associational quantities, all right? Now, what you see is whether a particular causal effect is identifiable or not will depend on what kind of causal graph you have and what kind of data you have available. And the other thing I want to say before we leave it for a break is we will be looking at multiple identifiability criteria. Some are complete and some are not complete. Now, what does that mean? Let's start with the complete identifiability criteria. So you have one of these criteria, you go to it and say, identifiability criteria. I have this causal graph, I have this data, and I'm interested in this causal effect. Now, the criteria comes and say, yes, identifiable, and it gives you formula. But if the criteria comes and say, no, it's not identifiable, in that case, because it's complete, that means not only did this criteria not figure it out, it's just provably not possible. All right? So if a complete criteria tells you yes, it's a yes. If it tells you no, it's no. Now, the discussion that is coming up next will end with a complete identifiability criteria known as the Duke calculus. But we're not going to start with this. We're actually going to spend time talking about other identifiability criteria that are not complete. And not complete means if they say yes, we trust them. But if they say no, it just means that that particular criteria couldn't figure it out, but some other criteria may. Now, you may say to yourself, should we bother with the incomplete ones if we already have a complete one? You'll see. The incomplete ones tend to be simpler, more intuitive, and they can give us insights into things. So they are useful. One of the more famous incomplete identifiability criteria is known as the backdoor criteria. We're going to discuss it in detail. Next, what's coming up next is given a causal graph and observational data and a causal effect. Is it identifiable or not? And if it's identifiable, how do we compute? So let's take our 10-minute break and we will delve with that discussion when we get back.